Got another year 13 rates of reaction question here you can use to test yourself with. So the link to the questions in the description of the video. Just click on that, try the question, and then play the video for the answers. Okay, so the question's all about the reaction between methanoic acid and bromine. We've got the equation there, and we're told the student carries out the investigation and uses a large excess of methanoic acid. So the purpose of that is to make sure that the concentration sort of remains constant throughout, so it's not going to affect the rate of the reaction. So the student's only investigating the change in concentration of bromine. So we've got this graph, and obviously we've got to work out the order of reaction from the graph. We've got to get the initial rate, and then we've got to calculate a value for the rate constant. Okay, so I've zoomed out a little bit so you can see the full graph. So the first thing I've got to calculate is the order of reaction with respect to the bromine. So we do that by calculating some half-lives. So try and go for a minimum of 2. I've gone for 3. So the first one I've done is to go from 0.01 moles per decimeter cubed of bromine to 0.005. And you can see that orange line there shows the time. So that's about 190 seconds. The second one I've done is just to go from 0.005 to 0.0025. So that time period there is 210 I'm getting. So it's there or thereabouts the same as the other one. And the third half-life I've calculated, done this one slightly differently. I've gone from 0.006 to 0.003. And that pink, the sort of difference between the two pink lines is another 200 seconds. So from my 3 half-lives, they're approximately 200 seconds. So I can say that it's first order with respect to bromine. So you can see I've written up there's those 3 half-lives. Okay, so 2 half-lives minimum. Reactions first order with respect to bromine because the 3 half-lives, that to that, that to that, and that to that, are approximately constant at 200 seconds. Okay, so the next thing we'll have to do is work out the initial rate. So you can see the blue line there. So I've drawn a tangent to the curve at time equals 0. So it just touches the curve at 0. So take it all the way down to the x-axis, and I can get my change in y, which is the change in concentration, divided by the change in x, which is the change in time. So change in y over change in x gives me the rate. So I got, remember tangents vary, so there's a range allowed here. I got an initial rate of 3.64 times 10 to the minus 5. So the units for that would be, remember this, concentrations in moles per decimeter cubed, divided by seconds per second. So don't forget your units. The range allowed, by the way, was anything between 3 times 10 to the minus 5 and 6 times 10 to the minus 5. Okay, so the final thing I've got to do is calculate the rate constant K. Now there's a couple of ways you can do it. I'll show you both ways. So you can do it from the rate equation, or you can do it from the expression ln2 divided by half-life. So from the rate equation, so we've established first order kinetics for bromine. It does mention, let me just find it, I'll highlight it. In this investigation, a large excess of methanoic acid was used, so they're repeating what they said at the top of the question. Under these conditions, the reaction is effectively 0 order with respect to methanoic acid. So, because of that, we can say that the rate equation is just rate equals K, concentration of bromine to the power 1. So we can rearrange for K, rate over concentration of bromine, substitute in the initial rate and the concentration at the start at T equals 0, which is 0.01, and I get a value for K at 3.64 times 10 to the minus 3. Units wise, well, we're dividing moles per decimeter cubed per second, so rate units divided by concentration units. Obviously the moles per decimeter cubed cancel and you're just left with seconds to the minus 1. So you could do it that way, or we establish the half-life at approximately 200 seconds, so that's what I'm going to use here. So K for a first order reaction, you can only do this for first order reactions, which this is, K equals ln2 over T half, so it's ln2 over 200. So you stick that in your calculator, and I got 3.47 times 10 to the minus 3. Again, the units obviously seconds to the minus 1. So slightly different to that, but both would be accepted.